Good morning, everyone. My topic is CSH, a post-quantum secret handshake scheme from coding theory. This work is authored by Zhuoran Zhang, Fangguo Zhang, and Haibo Tian. I am Zhuoran Zhang from Sun Yat-sen University, China.
Today, I'm honored here to share this work with you. As far as we know, CSH is the first post-quantum secret handshake scheme, and we think this work may cause lots of interesting discussions. My presentation will be organized as follows. First, I will show our motivation to do this work. Then, some preliminaries will be reviewed. After explaining the model and security properties of secret handshake, we will present our CSH scheme and analyze it. Imagine that Alice is an agent lurking in a criminal gang. Now, Bob is sent to this gang to connect with Alice. How could they recognize each other if and only if they do come from the same organization? The answer is to use secret handshake protocols. With the rapid development of quantum computing, many crypto systems become not safe anymore, so that the existed secret handshake schemes based on factoring problem or DLP problem. Thus, constructing a post-quantum secret handshake scheme is a worthwhile work. Now, let's begin with basic knowledge for error-correcting codes. An NK linear code C is a subspace of vector space over finite field FQ, where n denotes the vector length and k denotes the dimension of the subspace. We use the traditional Hamming weights as the metric of vectors. The code can be defined by a generator matrix or a party check matrix. The communication channel is usually noisy, and the received word may contain some error partitions. The decoding algorithm means to recover the correct code word from the noised one, and syndrome decoding means to find the error partition from the received word. Decoding problem and syndrome decoding problem are equivalent to each other, and they both have been proved to be NP-hard for general linear codes. Cfs Signature System is the most widely known code-based signature system. One of its variants is the Modified CFS system, or MCFS for short, which is proved to be existentially unforgeable under adaptively chosen message attack in the random oracle model. An MCFS signature of a message M is generated by hashing M and a random value R into a syndrome and trying to decode it. The security of MCFS system relies on the hardness of Gaupa distinguishing problem and syndrome decoding problem. Stan proposed a code-based zero-knowledge proof system whose security also relies on the syndrome decoding problem. This system is a three-pass prover-verifier protocol with chaining probability equal to 2/3. The prover can prove that he or she knows a secret vector x whose weight less than t, and each x is a syndrome of a code C. To do this, the prover first makes a commitment about x and sends it to the verifier. Then the verifier sends a challenge to the prover. Afterwards, the prover returns the response back, and the verifier will check whether the commitment is correct. Stats protocol can be transformed into a signature system by Fate-Jamir paradigm. The main idea is changing the random challenge into a value generated by a random oracle with the message. Now, let's take a look at the secret handshake model. Secret Handshake game operates in an environment which contains a set of groups managed by group authorities and a set of users UN to UM registered into some groups. Setup generates parameters and send it to GE. GE creates a group and the public is group public key. Add member is a two-party protocol run by users and GA, which adds a user to become a legitimate member of the group. GA will send the user's group credential to the user and adds his ID and credential to a list L. Handshake is executed by a pair of anonymous users UN and UM. The protocol takes the anonymous user's secret and some public information as input, and output 0 or 1 for each party. Trace member is executed by GA. It outputs the identity of the user when a transcript of secret handshake between two users is submitted. Remove member takes its current credential revocation list CRL and user's token as input. Whilst outputs an up-to-date CRL that includes the new revocation records. In general, a secret handshake scheme must satisfy the following security requirements: completeness, impersonator resistance, detector resistance, and unlinkability. Before describing the concrete CSH scheme, let's see the basic idea first. We know that stance protocol can prove one guy has a secret vector with low weight, while the output of CFS signature is such a vector with low weight. Intuitively, we can use CFS signature to sign a user's ID into a low-weight vector as the user's credential, and then, in the handshake protocol, the users can use stance protocol to verify their identity. However, stance signature can be public verified, which means that everyone can know that whether this signature is true or false. Thus, the key point for us to construct the secret handshake scheme is to modify stance signature in order to avoid public verification. Now, let's take a look at the concrete scheme. The create group step and add member step is actually a part of the CFS digital signature system, where the GA generates the group public key and group secret key. Then, GA will send a user's ID into a credential. In the handshake step, suppose a user U in group G1 and another user V in group G2 are involved. In round 1, U first makes a stance signature of his credential. The challenge part is the hash value of user ID and G1's group public key. To avoid public verification, you only send the response part, that is to say sigma U here, to V. After receiving ID U, CU, and sigma U, V first check whether ID U is in the CRL list. Then, V computes the challenge part by IDU and G2's group public key. Afterwards, we depart sigma U into response U, and then depart response U refer to the value of challenge. The calculation of CKU is similar to the verify step in stance signature, other than V can only compute a value but cannot check whether it is equal to U's commitment. Notice that in this step 1.2 and 1.4, V uses G2's group public key to compute the challenge and CKU. Thus, if U and V come from different groups, they will get different CKU. In the second round, V will send IDV, CV, and sigma V to U. This is the symmetric process just as round 1. After calculating CKU and CKV, U and V will send a response to each other. If they come from the same group, they will output 1 to illustrate they made a handshake successfully. A session key will be produced in this case at the same time. The group authority GE can trace member by looking up the member list L and remove member by adding the malicious member's ID and credential to the CRL list. Now, we will provide the security results on CSH as described before. Completeness means the protocol always outputs 1 when interactive participants belongs to the same group. The completeness of CSH relies on both participants can recover the CK part by their group knowledge. With the same group public key, U and V will share a same challenge value, and then we can recover the response of U's stance signature correctly. Thus, the same CKU will be shared, and so that the CKV. As a result, the completeness of CSH holds. For impersonate resistance, the outline of the proof is to build a sequence of games. If the adversary can break the impersonator resistance of CSH, we can use his abilities to solve a decisional syndrome decoding problem. Game 1 is the real game. If the adversary on behalf of a member in Group G succeeds in executing Handshake with the simulator, the output of this game is 1, otherwise it's 0. In Game 2, the simulator sets the group public key as H star in the S query, where H star is the party check matrix in the aimed decisional syndrome decoding problem. In Game 3, the simulator sets the hash value of IDA as S star in the aimed problem. The simulations of a hash function are the common methods just as those used in the proof of Cfs system. The proof of detector resistance is very similar to what we did before, and we will omit it here. The unlinkability of CSH is obtained by one-time pseudonyms. For each secret handshake, the users have to use a new credential. The main attacks to the code-based schemes are information set decoding attack and generalized birthday algorithm attack. We list the computational complexity of these two attacks to the CFS system here. To reach the security level of 80 bits, the parameters Q, M, K, T, kappa can be chosen at 2, 19, 11, 137 respectively. We can see that although the communication cost is huge, our CSH scheme performs well in the speed of executing one handshake protocol. Secret handshake schemes can be applied in e-commerce field, e-healthcare system, and many other information technique services, such as the transmission of confidential documents between company partners. With the arrival of 5G era, the data transmission speed is faster and faster. It only takes a few seconds to download a high-definition film. In this context, the communication cost is no longer the key factor restricting the application of secret handshake. Since the end member step has been finished before a handshake is requested, we can mainly consider the cost of the handshake step in the actual use. Thus, CSH is such a protocol with a high communication cost but small computation cost. For example, HDMI is an interface standard of HDTV, which can provide high-definition lossless transmission of digital video or audio signals. By using secret handshake schemes, the video providers can provide illegal infringement interface from matching their HDMI. Considering the fast speed of executing CSH handshake, our scheme may play a significant role in similar applications. To summarize, we combined the modified Cfs Signature System and Stance Identification System to construct CSH. Hence, more efficient variants of CFS system and stance system will lead to a more efficient secret handshake scheme. For achieving simple traceability and unlinkability, our construction still uses one-time pseudonyms. Thus, how to build post-quantum secret handshake schemes with stronger anonymity is still an open problem. As far as we know, this is the first time to use a generic Fate-Shamir type signature in constructing secret handshake schemes. This makes us consider whether it means that secret handshake can be built from any zero-knowledge proof systems, which may lead to a more generic framework. For future work, it is also interesting to build secret handshakes from other post-quantum cryptographic primitives, such as lattice-based crypto systems. That's all. Thank you for your attention.